Hello, good morning everybody. Welcome to PCM's webinar on rod string makeup. Firstly, thank you so much for taking the time out of your schedules to join us and myself and Paul and Benjamin for what hopefully is useful for common problems which lots of operators and end users face all around the world. My name's Adam Reynolds. I'm the head of sales at PCM Middle East in Dubai. We've got Benjamin Robert coming from Champs-Élysées at our HQ in France, and we also have Paul Skoczylas as our presenter today in Edmonton in Canada. Paul joined us in November 2019 as our ALS product champion, and before that he was with CIFA for 23 years as a senior engineering advisor. So I think some of you guys have had the benefits of Paul's extensive experience in the past, and fingers crossed he can be useful for you again today. I'll not keep you much longer. Just to make you aware, it's a one-way audio system, so we can't hear any questions, etc., from you guys. But down the right-hand side of the page, you should see some questions and answer boxes. So if you have any questions during the presentation, please just type your questions in there. We'll review them and then publish them so we can answer all those questions at the end. So I won't keep you any longer. I hope you enjoy the webinar, and I'll send you to Paul.
Okay, good. Thank you, Adam. Again, my name is Paul Skoczylas. I'm going to be talking about rod string makeup today. So looking through the list of registrations for this, a fair number of people and a lot of familiar names there. So hello again to everybody I've met before, and hello for the first time to those I haven't. And we'll start right away here. Sorry, I put the wrong date on this slide. It's because we did this 2 weeks ago for North America and Europe, and I didn't change the date, so apologies there. All right, just a brief outline, what we'll talk about, a quick introduction. I'm going to talk about some of the standards and recommended practices that are published in the industry. Talk about a bit of definitions, then the failures, and then we'll get to the real meat of this is connection makeup. So the main message that I want to get from today's presentation is if you're having rod string failures at the connections, this can be solved by changing how you make up your connections. So that's giving you the answer right at the beginning of the presentation, and I'm going to try and justify that over the next 20 minutes or so. At the end, I'll go through all the questions that people have asked. So Adam and Benjamin will go through, and they'll when you type in a question, they'll look at it and click the publish button so everyone can see it, and then at the end I'll go through and answer those at the end. So who am I? Adam gave a quick introduction, but I'm a mechanical engineer by training. I worked at CIFA for 23 years. I've been all over the world teaching PCP courses, and I've seen all sorts of different things. So yeah. One of the things I did in my previous job was rod string testing. I worked with several major rod manufacturers and a couple of minor ones as well, testing rods in an apparatus designed for doing torsional and axial load together at the same time, just like we have in PCP applications. And we learned a lot doing that testing, and I'm hoping to share some of that with you. I also served on the ISO committee that was writing a standard for PCP drive strings. That has not been published yet. It's still in a draft mode. It's kind of on hiatus since the last time the oil prices dropped. But before we get started, I just want to make one little note. I think the ad on LinkedIn for this presentation said I was going to solve all your rod string problems. I just want to clarify, I'm talking about rod string connection problems. There are certainly lots of other types of rod string failures that happen, and that's not today's subject. So we're looking at the connection specifically today. Okay, so here's some of the standards that are published. The big standard in the industry for sucker rods is API specification 11B, and the last edition of that was published in 2010. Generally, this is what people refer to when they're talking about sucker rods. There are also what people call drive rods, or depending on the manufacturer, you might hear different names for them. That are variations on the rod, or maybe actually sometimes completely different depending on which manufacturer you're looking at. But most of the rods are either following the API standard or are strongly based on it. The common variations that we'll see are a variation on the thread length, which I'll talk about a bit later, and the strength of the materials. There are some thread variants that some companies use as well. Next is API Recommended Practice 11BR from 2008, the latest edition, care and handling of sucker rods. There's a lot of really good material in this document, especially when it talks about handling, storage, and transportation. But I want to make it clear this document was intended for sucker rods being used for reciprocating applications, beam pumps. Some of the issues for PCPs are the makeup procedure. The overall procedure is good, but the amount of makeup is not correct, and there's a couple of details that we need to look at there in the procedure that we'll get into later. Also, the load calculations that are in that recommended practice, they're called modified Goodman diagrams. Those are specifically for the reciprocating application. There's no mention of torque strength in there at all. But overall, it's still a good document, and for especially looking at handling, storage, transportation. And then there's ISO 15136. There's 2 published parts to that, -1 in 2009 for pumps and -2 from 2006 for drive heads. Those documents have some good background information on rods in there. You'll see if you have those 2 standards, there's a lot of overlap between the description on rods in them, because they basically copied the same information, and the different committees, so they edited it a little bit differently, but there's still some good information in there. -3 is the standard that I was on the committee for. It's only in draft mode right now, and it's the one that if it eventually gets published will really be important for our industry, because it's specifically to rods being used to drive PC pumps. So it'll have some really good things in there, and to me the most important part of that, if it finally gets published, is coming up with ratings for sucker rods. How do we rate a rod for torque? Let's start with a couple of definitions here. So I hope you can you see my my mouse on here, so I can point to some things. If not, I'm going to try and use the numbers on the diagram. So this is a picture from API 11B, and we have the connection here labeled with number 4. The coupling labeled number 4 here, and then the pin, which is on the end of the rod, is labeled with number 6 here. And of course, they both have threads. There's a few different parts that we're going to look at here. This section here, which is smaller diameter on the pin, it has length LR and diameter D1. That is what we call, in the API standard, it calls it the stress relief. I usually call it the undercut, because that's the term I was told when I first started in this industry, but in the standard it says stress relief. This section is really important for beam pumps, but it doesn't matter so much for the PCPs, but we'll come back to that. The pin shoulder is this section here that has a diameter of DF, and the coupling face is the part that contacts the shoulder. A full-size coupling has a larger diameter than that pin shoulder, so the diameter marked by either 1 or 2 on this drawing would be a full-size coupling, and a slim hole coupling marked by number 3 here has the same diameter as the pin shoulder. So that's just some terminology. This undercut diameter is actually larger than the rod that goes with the same size of pin. It's actually larger than the next larger rod as well. So for a 7/8 inch rod, that undercut diameter is actually just over 1 inch, so it's bigger than the next size of rod. And I think that's important. It means that undercut section actually has a lot of strength to it compared to the rod body. So how does a modified pin, so these PCP drive rods out there that have a modified pin, how does it differ from an API pin? Looking at the ones that are still based on the API, like I said, there's some other companies make ones with tapered threads or square threads and things like that. But most of the ones you'll find on the market are very similar to an API with just a couple of little differences. So the 3 main differences you might see there is the length of the undercut, that's this section here, this LR, is shorter. But the LS, the total pin length, stays the same. And what that does is it means you have more threads. If you look at the way this drawing is shown, it looks like if you put some more threads on here, they're not actually going to engage on the coupling, but that's just the way it's drawn. Depending on the size of the connection, whether it's 7/8 or 1 inch or 1 1/8, you'll probably get between 2 to 4 or 5 more threads engaged with the reduced undercut and more threads. So more threads means you're less likely to see things like strip threads because there's more shear area there. The second thing we'll see is that the pin size doesn't match the rod size. So on a 1-inch diameter rod, they'll actually forge a 7/8 pin and cut the threads for a 7/8 pin. So you have a 1-inch rod with a 7/8 connection on it. And that reducing that diameter of the connection actually has some really good benefits in a PCP application. Reduces fatigue on the rod. It should reduce the amount of tubing wear you get as well. Not a lot, but a little bit. And it also increases flow area. So if you're dealing with viscous oil, that can be important. Also, when you get into the really big sizes, when you go to some areas in the world, we have really big pumps. They're using 1.25 or 1.5 rods. There is no 1.25 or 1.5 API rod. So they're actually using either 1-inch or 1 1/8 inch API pin on those larger rods. And the third difference is material strength. The API standard, the highest strength in the current edition of the standard is grade D. A grade D rod has a maximum tensile strength of 140 KSI. There are some high strength rods you can buy in the market that have a minimum tensile strength of 140 KSI. So that exceeds obviously the maximum for API grade D. So you can't call it API grade D, but there's nothing else to call it an API. So technically that can't be an API rod, even if everything else is the same. And then as the last note there, it says there's thread designs which are totally different and not called modified API. Some of the different companies have them. Like I said, they might have tapered threads or square threads. Some of the companies that sell hollow rods will have different threads as well. I'm also not talking about polish rod connections here. Polish rods have a slightly different thread type as well. There's a little bit of a taper to those threads, and I'm not talking about those here either. In general, I'm going to just make one more comment on definitions here. In general, when I say coupling, I'm referring obviously to the coupling. The pin is the part on the rod, and if I use the word connection, it means the two pins and the coupling together. I think I missed the point there. When we talked about that LS and those on that where LS stays the same, the reason they make LS stay the same instead of just making it longer to put more threads in is it means you can still use a standard API coupling. There's no difference between the coupling on a beam pump system and a coupling for a PCP drive rod if you make them like this. If you made the pin longer, you'd have to make the coupling longer as well. On one more note, talking about slim hole versus full size coupling, sometimes people ask, is the slim hole coupling not as strong? I would always recommend using the high strength material if you're buying slim hole couplings. Turns out the cost is about the same for most of the vendors, I think. To get a slim hole high strength coupling costs about the same as a full size standard material coupling. So it's definitely a wise investment to buy the high strength slim hole couplings if you're going to buy slim hole. So looking at rod string failures, what are the most common failures we see? The failure can be in the rod body or it can be in the connection. So in the rod body, we'll often see fatigue failures. This top picture here is a very clear fatigue failure. When you see this two distinct areas, you get this one very smooth area on the top and this rough area on the bottom. Anytime you see that, you know that's a fatigue failure. And in most PCP applications, where you're going to see that fatigue failure is in this picture right below it, right beside the coupling, right where the rod has reduced down to the rod body diameter, and you're just past the upset. Reasons for that are detailed. It's not the topic of this conversation, so we'll skip that for now. But that's where you're going to see fatigue failures most of the time. Corrosion, obviously, here's a couple of pictures of corroded rods. If you get a lot of corrosion in your wells, it's going to reduce the strength. You'll often get fatigue failures starting at these corrosion pits in the rod. So the final failure may actually be a fatigue failure, but it's clearly related to corrosion. And you'll especially see that with continuous rod, although it can certainly happen with standard rod as well. Wear. Most applications, rod wear is not a big problem, but I know there's some people listening today that actually have some pretty significant rod wear problems. Just because of the nature of their operation. Most of the time, where you get a hole in the tubing first, So you have to pull the tubing, and when you're pulling your tubing to replace it when there's a hole in the tubing, you should always be inspecting your rods and making sure you're not running anything back in that's badly worn or corroded. So it reduces those problems. But there are some companies that run with packers, which allows them to actually continue running when there's a hole in the tubing. And then you can end up going to the point where the rods eventually wear and break because of wear. But that's much less common. And then there's, so it says over torque here. One of the points I want to make is when we do testing in the lab, back at my previous employer, with the procedures we used there, the rod body always failed first when we put more and more torque on. So using our lab procedures, the connections, even a 7/8 slim hole connection on a 1-inch rod, the 1-inch rod would fail first. So if you're seeing failures due to over torque on the rod body, it's probably related to having material loss due to wear or corrosion. Usually you're going to see the coupling fail first. Also, if you've set your torque limit on your VFDs or whatever surface equipment you've got, if you set that to 80% of the manufacturer's torque rating, again, you should never break a rod body unless you've got bad corrosion or wear. So what I'm really talking about today is connections, because this is the easy problem to solve. Dealing with corrosion or wear, fatigue, those problems are more difficult, and we can work with you on those, but it definitely is a little more difficult. But the connection, we can solve these ones much more simply. The tricky part is getting the rig crews to actually do what we tell them to do. But I'll explain what the procedure should be, and then it's up to you to try to implement those in your companies. So connections can fail by being backed off. By that I mean unscrewed. So during backspin, sometimes you'll see couplings unscrew, or connections unscrew. Sometimes the couplings will split open if it's, and you'll see a bit of a bell shape on the end. The bell shape by its own is not a failure as long as the connection is still intact, but in extreme cases, it splits right open. More often, you're going to see sheared threads, and that's like we see in this bottom picture here, or a broken pin, like the one over in the bottom right. So these are the two more common connection failures. So how to solve those connection failures? Simple answer is to make up the connection properly. And there's 3 things you need to know to make up a connection properly. But before I get into these, let me just explain something. This type of connection, the API connection, has been used for, 100 years. It hasn't changed a whole lot in that time. It was never designed for PCPs. It was not designed to carry torque. It does work. Absolutely, if it's made up properly, it does work to carry torque. But the torque is carried by friction. And most of that friction has to be between the coupling face and the pin shoulder here. If you get good friction there, you get good torque capacity in your connection. So our maker procedures have to be designed to allow for maximum friction between those surfaces. So, how do we do that? If you remember high school physics classes, if we talked about friction, they'll say there's 2 things that friction depends on: the contact force between the 2 surfaces and the coefficient of friction. So we want to increase the contact force and reduce the coefficient of friction to get as much friction as we can there to increase our torque capacity. So to do that, 3 things. First, the connection must be properly cleaned. Most of the rod manufacturers will ship their couplings and their rods with some grease on the threads. That's to protect them from corrosion during shipment. You should not be running rods in the well with that grease on there, or oil. It should be cleaned off prior to installation, especially from the coupling face and the pin shoulder. That's very, very important. If you can clean it off with a solvent like Varsol or kerosene, that's good. Even better would be to use something like brake cleaner that you can buy from an auto parts store. They sell the same product in other stores as electrical contact cleaner. It's really good. I mean, it's a solvent, but it's a very volatile solvent that after you clean off the oil, it evaporates and leaves no trace behind, so you get a very clean surface. So the second thing is to use the proper lubricant and the proper amount of lubricant. And here, some vendors will say to use no lubricant at all. The purpose of using lubricant on the sucker rod threads is to prevent damage due to galling. Some of the manufacturers put other types of coatings on them. Sometimes it's a phosphate that's applied to sometimes to the coupling thread, sometimes to the pin, usually the coupling. And that's supposed to prevent the galling as well. So if you've got that, you might not need lubrication. But again, follow your rod vendor's recommended practice for that. What lubrication and how much. Usually it's a very, very small amount, less than the size of a pea. It doesn't take very much at all. You are definitely not using a brush to spread it all over, and you're not using tubing dope. It's a different product. Again, the rod vendors will tell you what product to use, and most of them will actually supply it if you ask, possibly at no extra cost, but you have to talk to them about that. One of the suggestions I heard from one of the manufacturers, which I thought was a really good idea, was apply the lubricant inside the coupling and not on the pin threads. They used to say put on the pin threads. The difference there is if you put too much on, if it's on the pin threads, when you screw the coupling on, it pushes that towards the coupling face. On the other hand, if you put it inside the coupling and then when you screw the pin into the coupling, it pushes that lubricant away from the coupling face and it'll end up in the middle of the coupling. So if you put too much on, it's not as much of a problem. So I think that's a good idea, and you should probably look at that. Absolutely critical that when you're making up the connection, there is no lubricant at all on that face. So you've cleaned it off and you haven't put more lubricant on that's going to be on that face or on the shoulder. And then the third step is to apply the proper torque before you run the rods in the hole. The most common way the manufacturers will say to do this is something they call circumferential displacement. And these pictures on the right-hand side describe this. These pictures come from API recommended practice 11BR. So you make up the connection hand tight and you draw a line across the connection. Normally you do it on both sides because the rod tongs will do both sides at once. Use your rod tongs, apply the torque, and then measure this circumferential displacement that occurs here between them. How far did that line move from hand tight to being fully tightened? And they'll actually give you little cards that you can use to measure this. So you can tell if your hydraulic setting on your power tongs needs to be increased or decreased. So we also talk about torque-based makeup, and in an ideal world, I would recommend torque-based makeup. Unfortunately, it's very difficult because most manufacturers or most rod tongs cannot measure torque very accurately at all. So if you can't measure it, you can't use that method. The most important thing is to make sure you put in more torque in than you're ever going to see during operation, though. If you can do that, you'll never have any problems. Having said that, if you put too much lubricant on or haven't cleaned it off, and you put in that much torque, say 1,200 foot-pounds on a 1-inch rod, which is more than you should ever put on that rod, you might break the couplings before you even install them. So it's still important to put the correct lubricant and not have too much lubrication. If you're using the circumferential displacement calibration cards, you need to check it regularly. So you want to do a few rods at the beginning of each job, and then do it every few rods after. Depending on who you talk to, the API recommended practice says to do it every 1,000 feet, which is every 40 rods. Most of the vendors will suggest something like repeating it every 10 rods. The more often you check, the better. If you're using manual rod wrenches, you should be checking even more often, just because it's much harder to be consistent with that. Calibration cards need to be appropriate for the application. They need to be for the right rod. If you're running PCP rods, different cards than if you're running beam pumps. If you're running a standard API rod that's actually designed for beam pumps, you should be putting more makeup in than what the recommended practice says. So they should have a card for that as well. The special drive rods that have the more threads and less undercut actually use a little bit less, because having the smaller undercut means you need less makeup to get more torque. So again, using the correct card. When we follow these procedures doing laboratory testing, the rod body always fails first. And I said that's even true when a slim hole 7/8 coupling is tested on a 1-inch rod. And it's still true with standard API rods. these drive rods that have the extra threads, those gives you some extra safety factor on there for when people do put too much lubrication on or don't make them up properly. But even with a standard API rod, a slim hole high strength slim hole 7/8 coupling is still stronger than a 1-inch rod body. So again, when you follow the procedures. I did a presentation at an SPE workshop in 2006. This was done in conjunction with co-authored with one of the rod manufacturers, and we did a test there. It was just on one size and one grade of rod, but I think the basic learnings from that test will apply for all the different sizes. So when we use the lab procedures that I just described, the failures were all in the rod body and at about 1.5 times the rated torque of the rods. So the couplings are certainly at this point damaged. They're probably showing a little bit of that belling, but they haven't broken. Then we did a second set of tests where we looked at what maybe a good rig crew might do without going as far as using lab procedures. So they wiped the pin in the shoulder with a clean rag but no solvent. So got as clean as you could without using solvent and made it up properly again with the correct lubrication. And just the difference between using a solvent and not using a solvent, now the failures are occurring in the connection. So they move from the rod body to the connection, but still at 30 to 50% more torque than what the torque rating of that rod was. So it's still good. And then we did a third set of tests where they put too much lubrication on or left the anti-corrosion grease or oil still in place and didn't clean it off. We did those rods, and they failed in the connection again at about 80% of the torque rating. So now we're substantially below the torque rating of the rods. So I think that's a pretty clear learning there. And again, I can't emphasize enough how important it is to clean those rods properly before installing them. Backspin. I've talked about overall strength of the rods, but what about unscrewing during backspin? Normally, torque during backspin is less than the operating torque. The couplings should not back off during backspin if they were made up properly. So I can't prove it to you. I haven't done the test to prove this to you, but it's my opinion that if you're seeing couplings unscrewing during backspin, that they were not made up properly originally, either too much lubrication or not enough makeup torque, or both, when they were initially installed. Quite often you'll see failures might not happen on the first startup, maybe not even the second or the third. You might see it later, just because of the events that happen in a well. So you start up the well, the rod connections might increase their tight. If they weren't made up properly, they might tighten a little bit. But if they don't fail, then sometimes they will. But if they don't, then you have a shutdown and there's backspin. And it might unscrew a little bit. But if it doesn't unscrew all the way, then you restart it and it's going to make up tight again. And you repeat that cycle 2 or 3 times, and you can eventually have a failure. Again, sheared threads, broken pin undercuts are what can happen if it doesn't unscrew completely. Of course, if that happens, you'll see that too. So it's my opinion that, again, if you've made up the connections properly, you won't see them unscrewing during backspin. Again, I said if you're having rod string failures at the connections, it can be solved by changing how you make up those rod string connections, cleaning them properly, putting the correct lubrication in. So I said this at the beginning, and I hope I've given you the information to justify that statement, and I hope this will be able to help you. I do want to tell a quick story before I wrap up here. There's a company somewhere in the Asia Pacific region, a small company that was running about some PCPs, and they were having lots of connection failures, and they called the rod manufacturer, and the technical representative went from Canada, and he flew out across the Pacific to this company, and he watched what they were doing, and he saw that, again, they weren't cleaning the connections properly. So he went with the rig supervisor, and they drove to the nearest auto parts store, and they bought a case of brake cleaner, and they took that back, and they used it to clean all the connections before they made up the next well and several wells after that. So he showed them that procedure, and they went from having lots of connection failures to having no connection failures at all. It's a very simple step to take to do that. It just takes a little bit extra time on on the rig floor. And that story, I actually heard it from both sides. I was talking to one of the oil company guys at an event, and he told me the story. And then at a trade show a little while later, I ran into one of the guys at the rod company I was talking, and I mentioned this story, and he said, "Oh yeah, that was me. I went there. I did that." So it was. So I heard the story from both sides there, and it matched up there. So it's again, cleaning the connections properly will greatly reduce those rod string failures. And again, clean them properly, lubricate them properly with just the tiny amount of the right lubricant, and then make them up to the correct amount of makeup, circumferential displacement or torque-based makeup, whichever you're using, probably circumferential displacement. So I've got my name and Benjamin's emails are on this presentation. This will get posted at some point. These slides will get posted to our website. And I think we're going to post the recording as well of either the presentation from 2 weeks ago or this one. We'll pick whichever one we like better and post it, so you can share it with your friends. So just keep an eye out on either on LinkedIn or on our website for that. And if you have questions, please feel free to ask by email. I'm happy to answer any emails. But now I'm going to turn my camera on, and theoretically, I'm going to go through and answer any questions. It looks like we have 9 questions that have been asked here, so I will go ahead and do that. Adam, did you turn me on to live here? Looks like I'm live. So, okay. First question, do you have more detailed specs which will differ PCM rod string from others? First off, PCM does not make rods. When we get bids from our customers that want rods, we will get those from third parties. If you have specific requirements for that, make sure that's in your bid or your request for quotes, and we will certainly do what we can to meet your requirements. If you haven't listed requirements or detailed requirements, and there's lower cost suppliers such as from China that are supplying rods that meet the requirements that you've asked for, then we can propose that in our bid. If you'd like to see a specific vendor or something like that, yeah, just let us know, and we'll make sure our offers meet your requirements that way. Second question says, how can we ensure rod string quality in order to disqualify poor products? Well, the first thing I would do for any rod vendor is to ask them what testing they've done, especially on their torque ratings. Where did they get their torque rating from? If they can give you a good answer for that, and if they can show you actual test results from that, then it goes a long way towards giving you some confidence in that. Obviously, if they're an API licensed manufacturer, even if they're selling you a non-API rod, like one of these modified connections, if they're licensed to make API rods as well, that's going to be some level of quality they have to meet to be able to do that. Beyond that, honestly, rod quality is not a major problem most of the time. Most of the failures you're going to see, if they're at the connection, they're because they weren't made up properly. If it's in the rod body, it's things like wear and fatigue, which are not the fault of the rod itself, but more just an application problem. You need to either accept that you're going to have those failures or improve designs using whether it's rod guides or continuous rod or whatever else to try to reduce those problems. Rod quality is not, I think, a major problem. The Chinese companies are a little newer in the market. I think there's a little less experience there. I have not seen any problems with that yet, but I know there's some countries are using a lot of those rods, and I haven't heard of any problems with it. So I think they're making rods to the API standard, and they should be decent quality. Perhaps the more established vendors might be better quality, but again, if you're making up your connections properly and designing the rod string appropriately, that shouldn't be an issue. Next question about Russian suppliers. Rods are designed for sucker rod pumps, not PCP. Again, probably most PCP applications in the last 30 years that have since the PCP really became big in the oil industry, most of those have been using rods designed for sucker rod pumps. These PCP rods that some companies use give a few extra benefits, maybe a little higher torque capacity. They allow you to use the slim hole connections, maybe to get a little more flow area and heavy oil, things like that. But you can still use the standard ones. If you don't have those PCP drive rods available in your region, whether it's Russia or China or wherever, you can still use the standard rods. And as I said, if you make them up properly, a standard API connection is still stronger than the rod body. So you can look at the different options that are out there for these variant PCP rods. But again, if what's available locally is standard API rods, again, make them up properly and they should work for you. Is the pin under the drive rod as per API? No, because that thread length is different, the undercut is shorter and the threads are longer, that is not an API connection anymore. So if you're in your bids, you're asking for a PCP drive rod that is API certified, there is nothing there on the market that can do that, because the PCP drive rods specifically make that modification to the connection, which is not defined in API, and therefore it's not an API rod. So yeah, be very careful about that. Everything else about the connection might meet the API standards. The thread form is identical. You can use an API coupling. All the tolerances are as per API. But there's that one difference, that difference in that LR length, and therefore the LS is the same. It's the LR that's shorter. So that's not an API rod anymore. Also, if you're buying a high strength rod, and I've seen this from bids, they usually use one particular manufacturer's designation for their high strength grade. They don't list the manufacturer's name. They just say, I want this grade of rod. That rod actually does not meet API standards because it's too strong, as I mentioned before. Again, if you're asking for this high strength API rod, that it's contradicting it. It's not an API rod. So I hope that answers the question. Someone says, in deep wells with close to max torque, is it okay to apply a small amount of thread lock or Baker lock? That's an interesting question. I haven't heard anyone say that before. Is it okay to do it? Probably isn't going to hurt anything. Again, if you've cleaned the connections properly and applied the correct lubrication, it shouldn't be necessary. But is it going to hurt it? Probably not. This next question says, what is the maximum acceptable number for screw the sucker rods? I'm not sure what that question is asking. I'm sorry. So I guess, sorry, I'm not, oh, Adam is saying something here. Let's skip that one and come back to it if we have. How much max torque should be applied during rod connection? Again, when we look at a maximum torque applied to the connection, if you apply more torque or just maybe a little bit more torque than you're ever going to see during operation, you should never have a connection failure during operation. If you got too much lubrication, it could fail on the rig floor making it up, but it won't fail once it's in the ground. So what I would look at is what's the torque rating for that rod. For a standard 1-inch grade D rod, most companies will say it's good for 1,100 foot-pounds of torque. So if I apply 1,100 foot-pounds or maybe a little bit more than that during makeup, I should not have a problem, especially since I should set my torque limit on my VFD to 80% of that, so 880 foot-pounds. So if I've made it up to 1,000, 1,100, 1,200 foot-pounds, and my torque limit on my VFD is 880, I should never have a problem with that connection. So again, that's my general recommendation. That's why I like the idea of torque-based makeup. And I get myself in trouble with the beam pump experts here, because the beam pumping guys who've been in this industry for 50 years, and I've talked with a few of these guys, you know, with all the gray hair and years of experience, and we continue to disagree on this topic because they're so focused on the beam pump application. What's really important there is to have the correct amount of stress in that undercut section. So for them, the circumferential displacement gives you that, because as you turn it a certain amount, the threads advance a certain amount. It doesn't matter what the torque is to them, it's how far those threads advance, and that's based on the circumferential displacement. So they are insisting that you have to use circumferential displacement. The problem with that is with torque, if you put more lubrication on, it takes less torque to get that circumferential displacement. So that's why it's very important to not put too much lubrication on, and if you can do the torque-based makeup, it's great. But again, the maximum torque, if the maximum torque during your makeup is more than you see during operation, your connection shouldn't fail in operation. Okay, well, troubleshooting rod makeup in PCP, how much length rod needs to be lifted? It doesn't need to be lifted any more than you would to put it in the rod tongs. So you're usually using your rod tongs on the rods, and whatever the requirements are for that. Does it have to be lifted for that? I don't think it does. I think it usually sits in the rod elevator on the top of the tubing there. So you don't need to do that. It's more just making up the. Sorry, I'm just I lost my question here. That question disappeared for some reason. Sorry. What causes fatigue in PCP application? Again, a little outside the scope of what I intended to talk about here. I could talk a long time about fatigue. I wrote an SPE paper a few years ago on that. I can get you the reference for that if you like. But fatigue in a PCP application is caused by the rods rotating through a bend. So when the rods are in a deviated well and they're bent to get through the deviation, as it rotates, one side goes from tension to compression and back. So you've got this cyclic loading, and cyclic loading leads to fatigue. So it's very different cyclic loading than what you have in a beam pump, where the axial load has this huge variation on the up and down stroke. In a PCP, the cyclic stress difference is very small, but it's millions and millions of cycles. And it just, if any fatigue cracks will just continue to grow for every time the rod rotates. The reason you see the fatigue failures most often just near the connection is because that's where the highest curvature is in the rods. And that's, again, a topic I could spend more time on, but a little bit out of scope there. But I certainly, if you have more questions on that, I'd be happy to answer them later on. Can you please, I presume, share more pictures of rod failures? And if you have simulation or actual tests. Of course, in my old company, I had lots of test data. Of course, at a testing company, that when you do a test, that's confidential to the vendors that we're doing the test for, so I wouldn't be able to share it even if I was still there. And I of course, now that I'm a PCM, I don't have that data. Having said that, I said earlier, if you're talking to a rod vendor about where they're getting their torque rating from for a rod, when they say it's good for 1,100 foot-pounds, where do they get that number from? They should be able to share that test data with you, or if they don't want to give it to you, maybe they can show it to you, just in person or over a web conference or something, and show you that test data so you can see, in fact, that it does survive that. In terms of pictures, I'll check on that. We did, when I was putting this presentation together, I did get a bunch of pictures. I chose the best ones to put in that one slide a little earlier on, but I'll see if I can put together a few more and maybe add it to the presentation that when we post that in a few days. So I'll see what I can find on that. I think we can certainly choose a few more pictures there. This question is it best to put the grease on the rod or inside the coupling? Again, I think that one of the rod manufacturers recommends putting it inside the coupling, and I agree with that recommendation. Previously, people always put it on the pin threads. So as long as there's not too much of it, it's fine. It's just if you are putting too much on, if it's on the pin threads, it will, when you put the coupling on, it'll get up to the face. So you have to watch that when you're making up a connection. If you put the grease on the pin threads, when you're making it up, if you see the grease moving out in front of the coupling face before it meets up with the shoulder, then you need to make sure you stop and you clean that out and make sure none of that gets onto the shoulder. But if you put it inside the coupling, you avoid that problem. Can I use the same sucker rod coupling for the rotor and polish rod, or is there special rotor coupling? Most PCP manufacturers and all the PCM rotors have an API sucker rod connection on them. So yes, using the same rod connection on the rotor that you do for those rods. I know that some vendors out there have some couplings with different threads on them. So if you're buying one of those rods or rotors from a different vendor, they will presumably supply you with the correct coupling to use for that rotor. But at PCM, they're all API sucker rod connections. Now, the polish rod, that's a different question. Polish rods do use a slightly different thread. And unfortunately, I forget the answer to the question. You can use, so there's polish rod couplings and there's sucker rod couplings, and one of them can be used in both places and the other cannot, and I forget which is which. So you can look that up either in a manufacturer's information, or it's probably in the API standard as well. I'm sorry I can't answer the question properly, but yes, there is a special polish rod coupling. You definitely want to use that on the polish rod, and you don't want to use it between standard sucker rods. So make sure you're using the right coupling in the right place there. What do you think is the best rod type of steel to run with a PC pump? Well, out of the different manufacturers, there's probably only a handful of different steel types they're using, 4 to 8 different steels that get used. Which is best will depend on your application. Some of them are going to be more corrosion resistant than others. So obviously some of them have higher strength than others. So it really depends on your application. I would never recommend running anything less than a grade D rod in a PCP application. So whatever they're using for grade C and grade K, I wouldn't use it in a PC pump. The grade D, yes, and the ones that actually are higher strength than grade D, yes. But the particular metallurgy will depend on your application. Are you in a corrosive environment? There may be some other factors there. I would recommend talking to the rod vendor about that. Talk to them about your application, and they should be able to recommend which steels are best for that. What are your thoughts on rod string connections that allow for full rated torque and forward and reverse rotation? I'm not sure which connections you're looking at. There's, other than the standard API or the modified API or the various tapered threads ones that are out there, all of those will unscrew if you put enough torque on them. Again, if you make them up properly, they shouldn't unscrew during backspin. But there is one rod on the market that uses that separates the torque, the axial load from the torque. So it's got extra pieces on the connection. It's not API at all. So the torque is carried by some square shaft or something like that, where then the axial load is carried by the threaded connection that goes on top. So that one will never unscrew during operation. I don't know what the field experience is on that yet. I'm not sure how many people have run it, so I can't say anything good or bad about it. The idea is nice. Totally get rid of all these connection makeup problems with that rod, but I don't know what the field experience is on that yet. Is there any issue to use the used rod for beam pump than for PCP? For used rods, if they're in good condition, they should be fine to use. The trick is making sure they're in good condition. So you need to check for any corrosion, you check for any wear on the rod body, check for damage on the threads. The most difficult thing to check for, which you can't do a visual inspection, is to see if there's any fatigue cracks. And this, whether it's you coming out of a PCP well or a beam pump well, it's the same thing. If there's fatigue cracks in that rod, they don't go away just because you're doing a workover. So reusing that rod allows those cracks to continue to grow, and you could have a premature failure because of that. So there are techniques they can use to look for those cracks, using things like eddy current testing and things like that, but that requires special equipment to do. It's not a visual inspection. Typically, I think most people don't bother, but there are some companies out there that do specialize in rod inspections, and they'll do the full inspection of the rod and make sure everything's good. But other than that, like I said, if it's a good looking rod, it's probably fine to rerun it. It's just those fatigue cracks are the one thing to worry about. And again, it doesn't matter whether it's beam pump or PCP, that's always going to be an issue for used rods. Is there a relationship between rod connection size and failure rate? Does size affect failure probability? That's a good question. If you've made up the connections properly, then the answer should be no. Like I said, a 1-inch rod with a 7/8 connection on it, if it's made up properly, under high torque, the rod body should fail before the connection. But if it's not made up properly, then that 7/8 connection is not going to be as strong as a 1-inch connection. So having the bigger connection size. So if you're using 1 1/4 inch rods, you can buy 1 1/4 inch rods with either 1-inch connections or 1 1/8 connections. If you can be sure your rig crews make them up properly every time, then the 1-inch connection will be fine. The 1 1/8 gives you a little extra safety factor. So again, the answer to your question is it depends on whether they're made up properly. If they are made up properly, then no, it shouldn't depend on it. But if they're not made up properly, you definitely have more safety factor with a bigger connection. For the same rod, more screw and unscrew effect on it or not, and how many? So when you make up the rods, does it affect them? You will see some differences. I should rephrase that. You won't see them if you're only doing circumferential displacement, but in the lab, when you're measuring torque, you do see a different makeup on the first run versus subsequent runs, because there's some little bit of deformation that happens during that first makeup. So subsequent runs don't seem to make much difference after that, though. As long as if you can visually inspect those rods and see there's no obvious galling on the threads, any damage on those threads, they're fine. I wouldn't worry about that. Doesn't matter really how many times they've been unscrewed and screwed together. If it's done too many times, you start to see damage on the threads. If it's visible damage, yeah, I would not rerun a visibly damaged rod or threads. But yeah, you will see, if you can measure torque, you will see some differences on that makeup. But again, if you're not measuring torque, don't worry about it. Use the displacement card, go to the correct amount of circumferential displacement, and don't worry about whether it's new or used, as long as it passes a visual inspection. For highly deviated wells, using drive rod and PCB is the only solution. Is there any other alternative, specialized rods with different geometry guides? So yeah, if you're in deviated wells, lots of problems happen in deviated wells. We get tubing wear, holes in your tubing will happen, and rod fatigue are the two main things that happen. And again, since I know there's people listening today where they have packers in their wells, so once they get a hole in the tubing, they can continue to run. Now, you know, a hole in the tubing. Now the rod body is rubbing against that hole in the tubing. There's a bit of a sharp edge there, and they can get some pretty significant wear on the rod right at that point. So all these things are essentially the result of running in deviated wells. The drive rod. The nice thing about the drive rod is with the smaller connections on there, whether it's a 1-inch rod with a 7/8 pin slim hole with a slim hole coupling, or use a 1 1/4 inch rod with a 1-inch pin, whatever. Having the smaller connection, what it does is it allows more of the rod body in contact with the tubing. So it helps unload the connection. Because if you got a big connection, all the contact force between the rod and tubing occurs at that connection. And the rod body may not actually be touching the tubing wall in between the connections. But as you go to smaller connections, it allows more of the rod body in contact. It spreads the load out, reduces the wear rate, also reduces the curvature, which leads to fatigue failures. The extreme case of this, of course, is continuous rod, where there's no upsets at all, and the rod just follows the tubing. It spreads the load out over the entire length of the tubing, which really works very well for continuous, or for reducing both wear and fatigue. The alternative solution, of course, is running rod guides. If you're putting rod guides, so the first level is at the centralizers. You can use these, spin through centralizers. I know PCM sells them. Other companies sell similar products. That reduces any wear at all at that contact point between the coupling and the tubing. They work great for that. Really reduce that. until such time as either that sleeve fails or you get a fatigue failure or these other things which still happen. The other option is guides that go onto the rod body. Now, when you do that, you're having more contact points. So instead of having all the contact at the connection, you can put 2 or 3 or 4 more points along the length of the rod. And again, spreading that load out over more points reduces the amount of contact force on each point and reduces the wear rate, whether it's on the tubing or on the rods, of course. Really shouldn't get very much on the rods at all because the rod's not in contact when you put guides in. It also helps for fatigue for reasons I'm not going to try and get into today, but the more contact points you have or the closer they are together, the less curvature there is in the rod, and it really reduces fatigue as well. So those certainly rod guides do help for that. You can buy rod guides that snap onto the rods. They work. They're not my preferred solution because they won't always stay in place, depending on things like your flow rates and temperatures and things like that. They can slide up and down. Even if it feels very tight when you install it, when it's got flow going past it in a tubing string, it'll push it up. And I've seen pictures of these things coming out of the wells where you get several of these connections. They're all sitting right beside the coupling, which really doesn't do as much. It still helps. You're still spreading it out over a larger area, but you're not protecting the middle of the rod anymore. Better is the molded on ones. Again, several different companies sell those. You're probably going to buy them from the rod manufacturer because they can install them in the factory when they're making the rods. There's a few different kinds of those. If you're buying molded on rod guides, make sure they're ones designed for PCP applications. If they have straight fins on them, they're not going to be good in a PCP. So you either want the spiral fins or no fin at all. And I would not buy it's my personal recommendation is not to buy the spin through guides that go onto the rod body. If it has a plastic sleeve inside it, because some of them have this plastic that molds onto the rod body and then a sleeve that goes over that. And my experience with those hasn't been good. There are some other options out there that don't have the plastic sleeve inside, which I think the field experience is probably pretty good on those, although I've only seen data from the people who sell them, so it's maybe a little biased. But I don't want to say anything bad about them because they might be just fine. Here's a question everybody always asks. What's the maximum deviation for a PCP application? There isn't a good answer to that, I'm afraid. I've seen dogleg severities as high as maybe up to 15 degrees per 30 meters or per 100 feet. That's a difficult application though. When you get dogleg severities that high, you're going to be dealing with tubing wear problems, rod wear problems, rod fatigue problems. People who are running like that often will have continuous rod, or they'll be running lots of rod guides, things like that. Ideally, if you can keep your dogleg severity below 3, you're going to get rid of a lot of problems, but in a deviated or horizontal well application, that's not realistic. You're not going to get there. So the higher that dogleg severity, the more of these problems you're going to have, whether it's rod wear, fatigue. And you just have to deal with that with rod string design using either continuous rod, the spin-through centralizers, reduced diameter connections, and the molded on or snap-on rod guides. So I think this is a repeat of a question. How much do you need to lift the rod during makeup? Again, just whatever the rod tongs require. You shouldn't have to lift it any further than what you need to put it in the rod tong. There's nothing else you need to do there. What do you think to get 2 parted and 1 continuous rod in the same time? That's always interesting. When I was younger in this business and people told me that they'd seen multiple breaks in a rod string, I was very confused. How can that happen? But I've seen them enough times now. It happens, whether it's continuous rod or standard rod, and I don't know what causes it. I suspect that what's happening is you've got 2 parts that are very, very close to failing. One of them breaks first, and then just the shock wave traveling through the rod causes the other one to break. That's my guess. I don't have an answer to it. I know it happens, but it's all I can do is give you a hypothesis as to why that is. Could you advise how many times we can rerun the rods? Again, The biggest question for me is what's the fatigue cracks that have happened in those rods. If you can inspect them, great. If you can't, you're looking for visual inspections of wear. Wear and corrosion are the big ones, thread damage as well. If you're a nice vertical well with no corrosion, no wear, there's effectively no real limit on how many times you can rerun them as long as they're in good condition. If you're in deviated wells, if you're having rod fatigue failures, that's when you want to be a little more careful and maybe counting how long those rods have been used. And if it had a very long run life, you might want to throw the rod string out or send it for inspection and run a new rods until you've got the inspected rods back. Because those fatigue cracks, you're never going to see them visually. So again, it depends on whether you're having those. But if the rods are in good condition, other than the fatigue cracks, there should be no reason not to run them again. But again, you can never see the fatigue cracks and you don't know if they're there. Really, that's a field experience question. Are you having fatigue failures in your field? If you are, then you better keep track of how long does it take for these failures to happen, and don't use rods that are getting close to that life. So someone's corrected me here. You can use polish rod coupling on a sucker rod pin. That makes sense because you need to connect the polish rod to the sucker rod. So that makes sense. What you can't do is use the sucker rod connection on the polish rod. So thank you for that reminder there. Yeah, most failure in the rod we have is from 1 inch to 8 inches from the pin. Yeah, that's almost certainly going to be fatigue failure. If your rods come out of the well and if you haven't damaged that surface during rig operations, you should be able to actually see that picture I showed earlier with the two distinct surfaces there. But when you see failures that are in the rod body but very close to the pin, fatigue is a pretty good guess. Is it okay to install rods pulled from sucker rod pump to install PCP? Well, I think I've answered that already. If they're in good condition, I don't see any reason not to. Which rod will be better to use in 2 7/8 tubing, 7/8 or 1? Depends on what your torque is going to be. So I would run the software out there that can do the calculations on the torque. If you're pumping a viscous heavy oil, obviously having the smaller rods gives you less pressure losses, but at the same time less torque capacity. So which of those is the more important factor? It depends on the situation. If you're pumping water, yeah, I'd probably go with the 7/8 rods, unless you've got some huge pump or something there that has higher torque. So yeah, again, I would do a software, whether it's PCM. We have our PCM design software, and everyone's familiar with the other software that's out there as well. We can all, whichever vendor you're looking at can do that calculation for you. What are the NDT tests which should be done before use of spindle and coupling? Other than thread inspections, and there's if you have the API gauges there's go and no go gauges for both the coupling and the pin. If you have those gauges, you can run them to look for any thread deformation or damage. Probably not something you're going to take out to the rig, but if the rack of the shop, that's certainly an inspection you can do. Other than that, it's visual. You're looking for whether it's thread damage or any corrosion or wear on anywhere on the rod or coupling. If you see a coupling that's got bad corrosion or wear on it, I definitely would not reuse that. A little bit, maybe it's okay, but if it's actual visual damage, I would probably not reuse that. The only other thing I mentioned is for the rod body is the eddy current testing, which again, that's normally going to be done in a specialized facility that has the equipment to do that. And that's looking specifically for the fatigue cracks. Should we use hammer to break up the joints? It probably doesn't matter. If you're using rod wrenches, standard rod wrenches should be fine for breaking out the joints. I'd prefer to use rod tongs, of course, just easier. But for making up the connections, that's where I would very strongly recommend using the power tongs for making up the connections. For breaking them out, it probably doesn't matter quite so much. Whatever tongs you're using, whether it's manual rod wrenches or power tongs, make sure you're using the right size. If you've got 7/8 rods, but you're using rod tongs for 1-inch rods, they might work, but they're going to do a lot of damage. And I've seen rods broken at the wrench flats, which the only two things that are going to cause that I can think of. One is damage caused by using the wrong tongs, and the other is manufacturing defect. But again, that's pretty rare. So yeah, use the right size. For breaking them out, less of a problem. For making them up, you're just not going to be as accurate in making up the connections if you're using manual rod wrenches. Do we have more? Oh, there's more. Sorry. I think. All right. How to reduce intensity of corrosion on tubing body? I'm not a corrosion expert, so that's getting a little beyond my area, I guess. I know there's people out there that run corrosion inhibitors. And one thing I've heard about corrosion inhibitors is it's always better to run continuous corrosion inhibitor than it is to do batches, especially in the PCP application, because the rods are rubbing on the tubing and wearing away any protection that's given from that. So I'm sorry, I can't give a better answer to that. It's getting a little outside my area of expertise there. Any new rod design in the market to be smaller size but with high torque resistance? The biggest thing on that right now is those PCP rods that you can get, again, using a 7/8 slim hole connection on a 1-inch rod, gives you that smaller size and still maintains the torque resistance of the rod body. There are some other ones out there. Tenaris, I know, has a specific rod connection. I'm not sure how much smaller diameter it is, if at all. And I mentioned that one that has where the torque is not carried by the threads, but again, I can't remember if it's a smaller diameter or not. But yeah, the smaller diameter is always good. You know, back at Seaford 25 years ago, they designed a special coupling or a special connection design that was for 1-inch rods, and it was this really small diameter. It never caught on. Instead, the manufacturers came up with using the 7/8 slim hole connection on it, which is still bigger than the one that Seaford designed, but people liked it a lot better because it was an API connection. Even if it was off size, it still was made up with API procedures, and the other one was not. It's needed special treatment, etc. So it didn't catch on. But no, I mean, like I said, for new designs on the market, I mean, I know there's that Tenaris one, and I know there's that Chinese one. I think it's called Exceed is the company that makes it. It has this torque's not carried by the threads. So you could check on what the diameter of those is. I don't know the answer. Do you have recommendation for space out when one is using a PCM pump and sucker rods from a different vendor? Again, PCM doesn't make sucker rods, so the rods are always coming from a different vendor. Space out is based on size of the pump, the load on the pump, the rod diameter, and the depth of the well. It turns out the grade of steel doesn't actually matter very much, whether it's grade D, high strength, or what. It doesn't matter as long as it's steel. So the space out will be the same for that size of rod, depending on, it doesn't matter which vendor that rod comes from. How much space out to use? PCM can give you those recommendations when you're buying PCM pumps. Some of the vendors will also have other ones. I've seen some vendors giving makeup tables that did not account for all the things it should have. So again, if you don't have the pump model, the well depth, and the rod diameter on your makeup tables, you're missing something. So I'd want to have a closer look at that and make sure you're getting the right information. And I know that the different software out there, again, whether it's PCM's PCM design software or the more industry standard software that everyone knows about, that will give you space out information as well. So I would always look at that for the specific application you've got. Okay, next, if our rotor is stuck in the stator and we're not using shear joint, then during so if you're gonna, if I'm understanding this question correctly, your rotor's stuck, you can't get it out. So what you're gonna do is you're gonna try and unscrew the rods by running them backwards, or you actually pull it if you're pulling extra force. So there's two ways that if you're pulling extra force, something's going to break, whether it's the rotor coming out or a rod connection or rod break. I'm actually not sure the answer if the connection. We always, when we did these tests, we always did them with, put a constant axial load on and twisted to failure. So I don't know the answer if what would happen under just pure axial load, if whether the rod would break first. The beam pump guys might be able to answer that question. But yeah, if you just want, I would recommend trying to unscrew it rather than trying to pull it. If the rotor won't come out of the stator, unscrew the rods, pull out whichever joint broke out first. You pull out those rods, and then you can pull tubing until the next rod comes to surface. But yeah, running a shear joint on the rod is a good idea to avoid that problem for sure, especially if you're running continuous rod. But how much contact load is acceptable in a PCP application? Depends how much wear you're willing to tolerate. The less contact load there is, the less wear there's going to be. So those numbers are again depend on your application. So again, the different software can help you estimate what that might be. And I know when you use the software, it doesn't always give you the exact answer to the number of days. But if you're comparing some things, if in your field you see these results and you use the software, it gives a different number. But when you change the design of the software, if it say changes the load by, if you change the load by half, you change the wear rate by whatever factor, you're probably going to get the same result in the field just relative to what your actual results are. So the software is very good on a comparative basis, even if it's not great on an actual basis. So again, it's one of these questions that doesn't have an answer. Do you want to see 6 months before a hole in tubing, 3 years before a hole in tubing, or is 2 months okay because your pump's not going to last that long? It depends on the situation. So again, not a simple answer to that question. Is it acceptable to tighten the coupling using a pipe wrench? I wouldn't. Is it acceptable? If you put the pipe wrench on the wrench flats, not on the coupling, or absolutely not on the rod body, never on the rod body. But if you put on the wrench flats and you make it up the right amount, it'll work. But the problem with pipe wrenches is they leave gouges in the steel, and that's just the point where failures can initiate from. So I would certainly not recommend the use of a pipe wrench. If that's all you've got, make sure it's on the wrench flats and be very careful. But I would not recommend that. Wax in tubing can cause rod fatigue. Not quite sure how wax would lead to the fatigue. Obviously, when you have wax in your tubing, you're reducing your flow area, you're increasing the overall stress on the rods as well. Which that higher stress can certainly lead to shorter fatigue life, but I don't think the wax, it's beyond that. I don't see that the wax would do anything. If you have some more information on that you'd like to share with me, and I can share some insights, I'd be happy to. But I'm not beyond, again, having smaller flow area leading to higher stress on the overall system. I'm not sure what that would be. Affecting rod connection to use hammer. Again, a hammer's, if you're putting a rod wrench on and hammering on it, probably not great. You're gonna have some more stress on that. But again, if you're using the right size of rod wrench and you're hammering on it, that's probably not going to do a huge amount of damage. I would certainly prefer to use power tongs, but if that's what you've got available, that's what you're going to do. Again, look for any damage, especially if you see any kind of damage on those wrench flats after you've done that, then you would not want to reuse those rods. Bigger tubing guarantee less fatigue for the rods? No, it doesn't guarantee anything. Depends on the application as well. If you're in a heavy oil, lots of viscous fluid or high rates, bigger tubing will reduce the load on the whole system, reduce the load on the pump, which reduces the amount of torque and axial load that the rods have to carry, and that will reduce the fatigue life, or reduce the fatigue stress and increase the fatigue life. But if it's a high water cut application, changing the tubing size is going to do very little to the overall stress on the rods and the fatigue on the rods. So I don't think it's going to make much difference unless you're in a viscous fluid.
Hi Paul, that's the last question for today, so we're going to leave it there. Thank you very much.
Okay. So I guess, sorry, go ahead, Al.
No, please go ahead.
I was just going to say, yeah, we're going to try and post this, the presentation and possibly the recording at some point soon. But keep an eye on our website and LinkedIn for further information.
Great. Paul, thanks so much for your time. I know it's getting very late in Edmonton, so we'll leave you to get some sleep. Guys, thanks for the guys that are still there and listening to us. We really appreciate you taking the time. Hopefully you found it useful. I apologise, we've had to cut the questions short. We didn't think there'd be quite as many as that. But if there's anything you're not sure about and there's questions not related to rod string failure, please reach out to any of the sales team or any of the engineering team that you know from PCM, or send us a question to ong.support@pcmals.com. And the SBU guys and the engineers can have a look at that for you and hopefully come back to you with an answer. We'd love some feedback. Anything that you think we could improve on, we'd really appreciate your feedback from today. And if there are any particular topics that you have common recurring problems with, and you'd like to suggest some topics that maybe we can put together a webinar on, just let us know. We'll be more than happy to consider that for future events. We are planning to run some more because it's not, it's obviously with the current lockdown situation globally, it's not great that we can't come and visit our customers and see your problems in the field itself. So please let us know if there's anything else that you would like us to cover. Other than that, thanks very much for joining us today. We've really enjoyed it. Hope you all have a great day or a great evening, depending on where you are in the world, and we look forward to seeing you again soon. Thanks, guys. Take care of yourselves. Stay safe.